Sir, shall we start, sir?
Yes, madam.
Okay,
Hello,
sir.
madam, you
Can we
can
start,
start.
sir?
Yeah, yeah,
Okay, sir.
yeah.
Good evening to one and all. I welcome you to the last parallel session of the day one of ICON 21. The session is on the theme nanotechnology for energy harnessing, transport, and storage. We have, in this session, we have 3 contributory lectures by Mr. Gobinda Gopal Khan, Sanjari Banerjee, and Ms. Suvani Subhadarshini, followed by the invited lecture 17 on spray drying of phosphate-based cathode materials for sodium-ion and potassium-ion batteries with advanced electrochemical performance by Dr. Abdel Fattah Mahmoud from University of Lake, Belgium. Before we start, let me introduce the chairperson of the today's session. It's my pleasure to introduce the chairperson, Professor D. Kingsley Jabbar Singh, who is the Dean of School of Mechanical Engineering, SRM IST. Professor's research interest includes engineering design, feature-based design, computer-based simulation of mechanical processes, and biocad. Professor has professional experiences like organizing secretary for the International Conference on the Mechanical Engineering on Advances in Mechanical Engineering, organized the professional development course on fuel cell technology in collaboration with Queen's University, Canada. He has also visited MIT to study the curriculum and teaching methodology under the faculty abroad program of SRM Institute of Science and Technology. With these few words, I request Professor Kingsley Jabbar Singh to take over the session.
Okay, thank you, madam. Thank you. Thanks a lot for the nice introduction. And now, I will briefly tell about this conference, okay, and the session. Okay, and see, this session is mainly apt for today's world. Okay, everybody talks about solar energy, and on the other side, battery. Okay, so I think though the number of participatory sessions, contributory lectures are very less. Okay, it is a good session per se. Okay, everybody talks about high energy harnessing and batteries. Okay, so with that, I think this is the apt one, and I welcome each and every one of you for this session, and also I welcome all the participants for this session. And now, with no further ado, let me go into this session. Okay, as the madam has stated, initially 3 lectures, contributed lectures are available. Okay, after that, one invited lecture. Okay, that is what the overall thing is. And then coming to the guidelines, guidelines, you can, each contributory lecture is planned for 10 minutes of presentation, which includes 2 minutes of discussion. So first bell will ring at the end of 6th minute, and second bell will ring at second bell, or the final thing, interaction start at 8th minute. Okay, so the participants are the lecturers are requested to note these things. Okay, this is most important because we are at the last session, and also everybody is tired from the morning itself. We are fed up with lot of knowledge. Okay, so let us go into that. Okay, now let me call the first participant. Okay, or the contributory lecture 1. It is the CL37. Okay, functional oxide nanostructures for solar energy harvesting. Okay, it is by Debishis Paul, Ayan Sangar, and Gobinda Gopal Khan. Okay.
Thank you, sir.
Yeah.
Now I request Mr. Gobinda Gopal Khan to share his PPT. You made the co-host now. Yeah.
Yes, thank you very much. I will now share my PPT.
Mr. Gobinda, you're not audible.
Can you hear me now?
Little bit more louder.
Yes.
Okay. Okay. I'll try.
I think keep
I'm
your
going
mouth
to
near the
share
mouth.
the.
mouth.
Is it okay now? Then
Yeah. Uh,
so I will share the PPT. Okay. Is it visible?
no. It says that you are sharing shared screen sharing. Started screen sharing.
Let me.
You can stop screen share and once again you can start.
Okay. Now share. Is it coming?
No.
Mm, that is the problem. Now share it. Mm, share.
Govinda ji can first
Yes,
open
yes,
your
yes.
PPT and then start sharing.
Okay. Yes, it is there.
So
Screen.
close your PPT first. Yes,
Okay,
yes,
is
yes,
it there?
yes, yes, yes,
Yeah. Now it is there.
Now it is coming.
yes.
I don't know very. So, okay, let me start. If it, am I audible?
Yeah. Audible but feeble.
Yeah. Little more louder.
Or
Is
keep
it
your
okay now?
microphone near to your mouth.
Yes, that's the thing I'm doing. I'm holding it. Can you hear me clearly now?
No.
No. Is it okay now?
Okay, go ahead.
Hello.
Louder, please. Okay.
Okay. So, I am Dr. Govinda Gopal Khan. I am working as assistant professor in Department of Material Science and Engineering, Tripura University, and it is my pleasure to give this talk for this conference, ICONN 2021. My talk is all about the engineered function of nanostructures for solar energy harvesting. And this is the outline of my talk, introduction and motivation behind the work, and function of the nanostructure for photoelectrochemical energy harvesting. And mm, then I will move to the main material where I'm in this talk. I'm going to concentrate on 1D nanostructures of titanium dioxide and engineered nanostructures. And finally, I will go for conclusions and acknowledgement. So first to start with introduction and motivation. The major energy challenge we have faced today's world is basically uh, we are using fossil fuels and all. So the fossil fuels are going to consume very soon, and huge environment pollution is going to be there related to it. So one solution could be the harvesting of solar energy in suitable way. So solar cells are very familiar for that. And now I'm going to talk about another approach, that is photoelectrochemical cell, where we can harvest energy in twofold ways, where not only direct conversion of solar light to electricity, as well as using that photoelectrochemical cell, we can generate some solar fuel with like hydrogen, maybe hydrocarbons. with the specific, using some specific techniques and instrumentation. So for photoelectrochemical material, uh, most important thing is the electrode, which is used for harvesting the energy. And for a good material to be, I mean, for equitable use for that, electrode, we need to, and the material should have basic properties like good absorption of solar light, effective separation of photo carrier after photocarrier generation, as well as rapid transportation and surface reactions on these things. So considering all these aspects and feasibility and all, mostly the oxide semiconductors are mostly used as photoanodes, because there are two types of photoelectrodes. One may be photoanode, another we can use as photocathode. So I'm not going to the details of that basic definition and so on. We are so considering these, we are now going to focus on one dimension titanium dioxide nanostructures, where titanium dioxide has earned its interest as a photoanode for a long time, and since the first work of Fukushima Honda, back in, almost 30 years back. So now 1D titanium dioxide nanostructures are getting important because 1D structures has large surface area, one-dimensional structures, and most importantly, they have unidirectional charge transportation behavior. So we can consider these things in that way. And another thing is that overall, uh, but titanium dioxide, but titanium dioxide is
Dr. Gobinda, sorry to interrupt
yes,
you. Your
yes,
voice is not at all audible, sir.
not at all.
Your voice is not at all audible.
Should I use now? Now is it okay? Huh?
It's very feeble. We're not able to hear you clearly what you're
Hello.
talking on.
Can you hear me now? Huh? No? Am I audible, man?
You're audible, but very feeble.
Uh, I'm just in front of a laptop and I don't know. Is there any problem?
Okay,
Is
sir,
it
continue.
okay? Okay. So, um, okay, let me continue. So, okay, I will try to be at a high of my, speech. So the thing is, now we are going to concentrate on titanium dioxide nanostructures. That is mostly one-dimensional. But the problem with the titanium dioxide nanostructures, that is, it has a large bandgap region, poor visible light absorption thing, obviously, poor charge carrier separation, and higher recombination of charge photogenerated carriers because of low conductivity on this thing. For these reasons, we need to do little bit of surface engineering or other engineering so that we can improve the photoelectrochemical properties of based on the titanium dioxide nanostructure. So now on this backdrop, we have designed few electrodes uh, to make this thing photoelectrodes suitable for solar energy harvesting or solar fuel generation. So one of the works we have conducted recently was hybrid structures based on bismuth ferrite and titanium dioxide nanostructures, where bismuth ferrite nanoparticles are like structures are anchored on the surface of titanium dioxide nanotubes prepared by wet chemical route, and the structure sometimes something which looks like this, and uh, this ecstatic pattern to confirm the fabrication of the structures with suitable crystallography and all. And we also have conducted energy fielded TEM studies to confirm the distribution of the elements on the surface of the nanotubes. So as well as X-rays was conducted to study the chemical composition of the materials we have prepared. So it confirms the fabrication of the suitable anchoring of nanoparticles on the surface of base of sterile nanoparticles on the surface of pure titanium dioxide and all. Now we have conducted the photoelectrochemical tests. So you can see the difference here. Um, and the photo, that is the photocurrent densities have been plotted against the voltage. This is the general approach we test the photoelectrodes. Now we have calculated the photoconversion efficiency, that is applied bias photoconversion efficiency, as well as photo switching properties of the electrode, actually the electrodes. Now we can see that um, photoconversion efficiency, photocurrent density was about for the hybrid nanostructures was 480% higher than the pesticide HCI2 material.
Dr.
And
Gobinda,
yes,
sir, you have 2 more minutes.
okay, I'll finish this thing, no problem.
Yes.
So as well as we have tested the visible light absorption, UV visible light absorption property of the materials and all. From this study, we can conclude that because of the formation of PN type heterojunction, because titanium dioxide is N type, where P type, but bismuth ferrite is P type. So because of the formation of the PN type heterojunctions, the and light absorption improves in the materials, and this is how the photocarriers are generated and electron hole pairs get separated, which leads to the oxidation of water at the electrode. So this is the gist of that. I'm skipping the other work for the timing. So the conclusion is, we can do a little bit of surface engineering or something like that. You can go for building new heterostructures, something like that, which will basically improve the electron light absorption property, generation of photocarriers, as well as separation. So we can engineer the electrode, design the electrode accordingly to get all these things uh, suitably done, so that the performance of the electrode we are working on can be improved. So this is all. I would like to acknowledge my students and as well as my funding agencies for supporting my work, and, and that's all. We are talking about the sustainable development and all, so we need to be very
Okay.
careful. With the thing.
Okay.
And
Now it is
that's all.
open for discussion.
Yes.
The participants can ask questions. Yeah. Madam, someone has raised question hand, it seems.
No, sir.
No. Okay.
No. No. No questions in the chat box also.
Okay. Anybody
So,
has any questions?
I'm sorry for that low voice. I don't know. I still cannot recognize this thing.
Okay.
I don't know how much audible it was for you. I'm sorry for that.
Can I know what surface structure you have studied?
Sir, this is one of the works I have presented. It is titanium dioxide nanotubes mostly,
Okay.
which was anchored with P-type bismuth ferrite nanoparticles.
Okay.
So it is a kind of 3D structure.
Okay.
Okay.
Okay. Thank you. So, ma'am, can we wind up? Can we go to the next one?
yeah. Yes, sir.
Yeah.
Yes, sir.
Okay. Thank you. Govinda Gopal. Okay.
Yes,
Thank you.
yes. Thank
Thanks
you,
a
sir.
lot.
Thank you.
Okay.
Thank you.
Yeah, we will move to the next contributory lecture, CL38. Okay, modifying the photocatalytic property of ZNO based photoelectrodes by introducing Fe2O4 nanoparticles. Okay, Sanchari Banerjee R and Tangavel, okay, Indian Institute of Technology, Dhanbad, or Mines, India.
Ms. Sanjari Banerjee, is she present here? Mr. Tangavel? Contributory lecture 38. So shall we move on with the next
Okay.
lecture?
Okay. Okay. Anybody is present for 38? Anyone? Mr. Tangavel or Chanchari Banerjee? No. Okay, we will move on to the next one. Okay, next session lecture is CL39, hierarchy dependent NISCSE hollow nanotubular architecture decorated on NIO nanoflowers as a binder-free cathode with superior capacitance for high performance asymmetric supercapacitors. Whether Suwani is present or Deepak Goswami or Narayan. Anyone is there?
Suwani, unmute yourself. Suwani Subhadarshini, unmute yourself.
The second speaker is present, sir. Sanchari Banerjee.
Okay. Then
Sanchari Banerjee, can you unmute your mic?
Hello.
Yeah.
Yeah. So sorry for the inconvenience caused. Now it is the CL38. Okay. It will be presented by Sansari Banerjee. Yeah, you can go ahead.
Sanchari, you can start your screen sharing.
Okay. Is it visible?
Yeah.
Yes.
Should I start?
Yes.
Okay. Good evening, everyone. Today I'm here to present my work entitled Modifying the Photocatalytic Property of Xetanol-based Photoelectrodes by Introducing Fe2O4 nanoparticles. Scarcity of energy resources is the greatest problem faced by mankind in this century. Splitting of water into its constituents, hydrogen and oxygen, in a photoelectrochemical cell is considered as a potential sustainable path for generating renewable hydrogen gas. The application of potential equals to 1.23 electron volt is an essential criteria to carry out the water splitting phenomena via photoelectrochemical cell. By suitable engineering of photoelectrodes, is possible to achieve water splitting under illumination without applying electric field. A large number of semiconductor materials like metal oxides have been identified as photoelectrode materials for PEC application. In this work, a low-cost method was opted to fabricate hematite as a shell layer on the surface of ZNO nanorods as a post-shell nanostructure electrode for PEC solar cell application. The ZNO nanorods on conducting substrate and hematite nanoparticles have been prepared by simply dipping ZNO nanorods into MgFe2O4 nanoparticles coupled ZNO post-shell nanorods heterostructure. that can enhance the improved photoelectrochemical properties. The surface morphology, optical property, photocurrent, and photoelectrochemical activity of this heterostructure photoelectrodes under visible light irradiation have been studied. This XRD pattern of ZNO nanorods and MgFe2O4 coated ZNO nanorods grown on glass substrate has been presented here. The obtained spectra have been indexed with JCPDS card number 361451 of pure phase Wurtzite ZNO structure. This indicates that the grown bare ZNO nanorods have the hexagonal Wurtzite structure with high crystallinity. After coating MgFe2O4 nanoparticles, some of the diffraction peaks of hematite are visible. However, the diffraction peaks are weaker compared to bare ZNO1. The unmodified ZNO nanorods and MgFe2O4 nanoparticles modified ZNO nanorods have been analyzed by FSM to investigate the surface morphology. The grown ZNO nanorods are vertically oriented, well-aligned hexagonal structure of almost uniform size with smooth surface. Now, the optical properties of semiconductors have an important role in the photoelectrochemical solar cell. From figure, it is visible the absorption edge of bare ZNO nanorods and hematite nanoparticles based thin films were at about 390 nanometer and 460 nanometer, whereas the ZNO hematite heterostructure shows an obvious red shift compared to bare ZNO nanorods. With increase in hematite layer thickness in the heterostructure, it has been observed that the ZNO nanorods, hematite nanoparticles, have higher absorption in the visible light as compared to ZNO. The photogeneration of electron-hole pair and charge separation are the essential conditions required for photoinduced redox reaction by semiconductor electrodes. The initiation of redox reaction can occur due to depletion layer in the semiconductor solution interface and with external biasing. In order to explore the electrochemical behavior, photoelectrochemical behavior of samples, ZNO nanorods and magnesium Fe2O4 and ZNO nanorods heterojunction structure as photoanodes, a platinum counter electrode and the AgAg cell reference electrode was dipped in 0.1 molar NaOH aqueous solution, which was used as the electrolyte, were used as the electrode in the photoelectrochemical cell. So figure represents the LSV IV curves collected from bare ZNO nanorods and array and the hematite ZNO nanorods heterostructure with and without illumination. So MgFe2O4 ZNO heterostructure grown on 1 hour dipping condition showed the highest photocurrent density with high IT current and time stability upon light illumination. So research synthesis of a new material structures and developing novel physical measurement methods can open a variety of opportunity for catalysis, photoconversion, energy storage, and biointerface. So thank you.
Now the forum is open for discussion. Participants can ask questions. See, the session should be interactive, so kindly interact with the other.
So one question is there in the chat box. What about the stability of the electrode?
Yeah, I have shown the stability. So in this one. And for 3000 seconds, I have performed also. So it is showing stability in a good manner, but that one I have not shown, but from 50 to 100 seconds. And then again, the light was off and again I switched on. So it showed better stability.
Ms. Sanchari, you have one more question. What will be the Fermi level of the zinc oxide, magnesium iron oxide, increased or decreased? How is it important?
Actually, conduction band and valence band I haven't calculated, so I'm not aware of this.
Okay, regarding the stability,
Yes.
have you tested it for us?
Yes, maybe for 2.5 hour I have tested it, so it showed better stability up to that time.
Any other questions?
Okay, no more questions means shall we go to next session?
Yes, sir.
And that is, yeah, and the contributor lecture 39. Already I have told the name.
Yes.
Anyone is available?
Yes, sir. Ms. Suvani Subhadarshini is available.
Okay, Suhani Suhadashini.
Ms. Sanjari, you can
Yeah,
stop sharing. Thank you. Ms. Suvani, you can share your PPT.
Yeah.
Okay.
Yes, ma'am. Ma'am, are the slides visible?
Yes.
Okay. Good evening, everyone. I'm Suvani Shubhadarshini from IIT Kharagpur. I'm going to present on the topic hierarchy-dependent NISESE hollow nanotubular architecture decorated or NIO nanoflowers as a binder-free cathode with superior capacitance for high-performance asymmetric supercapacitors. Now, coming to some of the basic questions as why do we need energy storage devices? The answer is in order to move towards a better, sustainable, or they say sustainably balanced ecological environment where we do not depend much on the conventional energy sources. And why do we need supercapacitors? We need supercapacitors because they deliver really good amount of power density, but they lack in terms of energy density. Why do we need battery type of materials? Because they deliver good amount of energy density. Now, is there a way that we increase the energy density of a supercapacitor without compromising on the power density of the supercapacitor? Then the answer is yes, with the help of a hybrid supercapacitor. Now, as the name suggests, the hybrid supercapacitors are made up of two different kind of electrode. One is the supercapacitor type and one is the battery type. Now, this equation, which is ED is equal to half CV square, where ED stands for energy density, C stands for capacitance, the specific capacitance, and V for the voltage window. So here you can see that ED is directly proportional to the capacitance of the material as well as the voltage window. Now, how I've incorporated these two things into my work, I'll be discussing later. Now, coming to the synthesis part, I've synthesized three different electrodes. One, I've directly taken nickel foam as a current collector. I've synthesized nickel oxide nanoflowers over it. On the second one, I've grown nickel selenide nanotubes. And over nickel oxide nanoflowers, I've grown nickel selenide nanotubes and just changed the hierarchy. Then for comparison purpose, I have left one electrode in a nickel oxide nanoflower format. Now, coming to the results and discussion part, the figure A, E, and I show the XRD analysis of pure nickel oxide grown over nickel foam and nickel selenide and nickel oxide grown over nickel foam current collector. Figure B, F, and J show the survey scan of the pure and the composite electrodes which have been synthesized. Figure C, C and D show the XPS analysis of which shows the presence of nickel into different oxidation states. And similarly for the composite samples also, we have seen the presence of nickel into different oxidation states and selenium into different oxidation states again, which is accounting to selenium 2 minus and selenium 0. Now, coming to the FESEM micrograph, what we have seen is for the sample A, which is the pure sample, the nickel oxide nanoflowers grown over the surface of the current collector. We saw a nanoflower-like morphology. In the figure, D, E, and F correspond to the second electrode, which was we have grown nickel oxide nanoflowers over the nickel selenide nanotubes. Here also you can see the morphology was retained, and figure G to J show the nickel selenide nanotubes which have been grown on nickel oxide nanoflowers. So here there's a reversal in the hierarchy. To confirm the nanotubular structure which have been grown on nickel oxide nanoflowers, we also took the cross-sectional FESEM analysis. Here you can see the nanoflower as well as nanotube structures both. Now, coming to the HRTM micrograph, again the morphology of the pure sample, the nanoflower structure was confirmed, presence of nickel oxide plate planes were also confirmed from the despacing analysis. Then the EDX analysis also reflected similar results. And this figure 6 shows the HRTM micrograph of the nickel selenide nano flowers grown over nanotubes. And the next figure shows the HRTM micrograph of nanotubes grown over the nanoflower structures. And similarly, nickel selenide, and nickel oxide planes were found in my material. Now, coming to the electrochemical characterization of the electrode synthesized, figure A corresponds to the CV of the pure sample, and B and C correspond to that of the composite sample. Now, comparing the CV of all the three samples, what we found was that nickel selenide nanotubes grown over nickel oxide nanoflowers showed comparatively better properties than the other two electrodes. Similar kind of results were also reciprocated in terms of the GCD curve. And we also seen the cyclic capacitance retention of around 94%, 94.24% even after 2000 charge discharge cycles. Now, quickly coming to what are the advantages of fabricating the hierarchical structure directly on the surface of the current collector. One is we get extensive surface area, then we get porous 1D nanotube channel for ionic transport, the conductive nano architecture for electron transport, high aspect ratio for shortened diffusion path, smooth interface for high mechanical strength, and finally the in situ growth on the current collector enhances the conductivity and capacitance. Finally, coming to the device fabrication part, out of all the three electrodes, I've already shown that the nickel selenide nanotubes grown over nanoflowers, nickel oxide nanoflower morphology showed the best performance. So we have taken that as a cathode. Activated carbon on a nickel foam, we have taken it as the anode, and we have separated them with a filter paper in a 1 molar KOH electrolyte solution, and we have made a pouch cell out of it. Then this is the CV performance of individual activated carbon, and this is corresponds to the NISAC at NIO electrode. Now, this is the beauty of a hybrid supercapacitor, where we were able to increase the voltage window, which is directly increasing the energy density of the material. Coming to figure C, we have also tested the stability of the electrode or the device, you can say it, different potential windows. We found that device could be used till from 0 to 1.6 volt. Figure D shows the CV of the device from 10 to 100 millivolt per second scan rate. Here you can see the pseudo rectangular kind of shape, which is characteristic of a hybrid material. Figure E shows the GCD curve of the device from 5 to 30 ampere per gram. Here the steep slopes also correspond or indicate towards the hybrid performance of the device. Now, coming to the cyclic retention, we found around 92% of capacitance retention after 10,000 charge discharge cycle, which is highly desirable for any kind of device. Figure B shows the Nyquist plot showing the solution and the charge transfer resistance corresponding to my material, which was also less, like around 0.2 to 0.4 respectively. And you can also see before and after cycle, the value does not change drastically. Figure C shows the Ragon plot of the device, of my device, along with other published reports. What we try to do is we try to achieve a good amount of energy density without compromising with the power density of the material. Then figure D shows the specific capacitance as a variation of current density. You can see even at high current density, around 80% of the specific capacitance is retained. Then finally, the real life practicality of the device was demonstrated by lighting a red LED and a PC cooler fan. So coming to the conclusion, a facile synthesis technique was developed by the direct growth of nanostructured electrodes on nickel foam current collector. Then electrochemical evaluation has been carried out for all the electrodes. Ni, Se, NiO, NF shows best electrochemical attributes. A hybrid supercapacitor device has been fabricated taking Ni, Se, NiO composite electrode as cathode and activated carbon as anode, and it worked at an extended potential window of 1.6 volt. The device delivered specific capacitance of 108.1 Fat per gram at 5 ampere per gram with energy density of 37.94 watt hour per kg at a power density of 875.30 watt kg inverse with an capacitance retention of 92.7% after 10,000 charge discharge cycles. The real life practicality was demonstrated using a red LED and a PC cooler fan. I'd like to acknowledge the SRM Institute of Science and Technology for giving me an opportunity to present my research work. I'd like to express my sincere gratitude to my supervisors and IIT Kharagpur for their endless motivation, support, and lab facilities. These are my references, and thank you.
Yeah, now the floor is open for discussion. I think there are so many questions, I suppose.
Yes, sir. The first question is, what is the source of the current? Any leakage current or any other things? It was asked.
Source of the current? I did not get the question, ma'am.
Someone has posted it.
Source of current for the synthesis, or I've used a 3 electrode system. Like if I do not know if I'm going the right way of answering, but I've used a 3 electrode system, the conventional ones, the AGCL as the reference one and platinum as a counter electrode, and this individual the NISC or NIO as a working electrode.
The next question is why there is a certain drop in the discharging curve of device.
Yes, the IR drop here. Yes. Yes, there are actually there are, we what we examined is we saw some kind of black particulates which corresponds to the precipitation of nickel selenide, or you can say nickel oxide in the form of hydroxides in the sample. So yes, we are working on it in order to decrease the IR drop in the GCD curve.
How did you fit the XPS data?
How did I?
Fit the XPS data.
It was a Gaussian fitting. Yeah, Gaussian fitting. A Gaussian fitting curve of the XPS.
I think no more questions, sir.
Okay, thank you. Thank you, Ms. Sirvani Subhasundari. Yeah.
Thank you, sir. Thank you, sir.
Yeah, thank you. Yeah, I think now we have come to the end of contributory lectures. Okay, we have seen all three lectures are presented in the forum. Okay, the first one talked about the functional oxide nanostructure developmental work or synthesis work. And in the second one, they have developed again a nano electrode and they have synthesized the things. And third one, they have gone from electrode synthesis to the fabrication of the device, and they tried to establish something. Okay, with red LED has been blown and a fan has been working, it seems. Okay, so it is a very good session. Okay, all three members were present, and I congratulate each one of them. We are finding it very difficult to segregate which one is best or whatever it is. Anyway, all are good. Okay, I also thank all the participants for this session. Okay, for the taking the time and attending this session. Okay. Okay, thank you. Is anything else you want to say, Dr. Angeline?
Sir, we'll move on to the invited lecture,
Yeah.
sir.
Okay.
So now I request the chairperson, Professor Kingsley Jabbar Singh, to introduce the invited speaker.
Yeah. And
Sir, you're not audible, sir. Hello.
am I audible, ma'am?
No, sir. Now only
Okay.
you're audible.
Now audible.
Now
Okay,
you're audible.
okay.
Okay, sir.
I am happy to introduce the speaker for this invited session, Dr. Abdul Fatak Mohammed. He is working in the Department of Chemistry, Faculty of Science, the University of Leeds, Belgium. His research interests are development of electrode materials for alkaline ion batteries, electrochemistry and Molecular spectroscopy, nuclear resources, and neutron scattering techniques. Okay, he has got some awards also. Dr. Mohammed has received his PhD in material science in 2012 from Cadi University, Morocco, in collaboration with Montpellier University, France, and the Institute of Material Science, Madrid. In December 2015, Abdel joined the University of Leeds, where his work at green mat is the synthesis and characterization of new electrode materials for rechargeable batteries, and mainly the volarization of the silicon extracted from solar panels as anode material for lithium-ion batteries. His H index is 17 and his citation is 774. With this few words of introduction, I request Dr. Muhammad to go ahead and present. Yes, sir.
Yeah. Okay, thank you very much, the chairman, for this nice introduction. And thank you very much for the organizers, mainly my colleague Sandeep Kumar, for the kind invitation to this very nice conference. I visited India 2 years ago, but this year, unfortunately, because of the COVID situation, we can only make it online. So I'm very happy to be here today and to present my work mainly on the spray-drying of phosphate-based cathode materials for sodium and potassium-ion batteries with advanced electrochemical performances. So I will just give few words about our core business of our research unit, which concern the study and the development of powder materials with controlled microstructure. So here in our lab, we are trying to control the microstructure properties either of powder or of films by making coatings in order to enhance their properties and facilitate their use in different applications. For that, we are starting either from solution or suspension. We are studying the solution and suspension to try to optimize the properties. And then we are using different techniques in order to prepare either powders or films. We are preparing this powder for different applications, including mining and metal materials, powder for food. We are developing mini powders for food. We have also a 3D printer. We are making the recycling as the example that was mentioned by the chairman, the recycling, for example, of silicon from the end life solar panels and reuse it as anode material for lithium-ion batteries. We are also preparing different drugs, materials for health, in order to enhance their performances. And my talk today will concern mainly material for energy. Indeed, we are very active in the field of the development of cathode and anode and also electrolyte material for lithium-ion batteries, sodium-ion batteries, potassium-ion batteries. And recently, we start another research topic, which is zinc-ion batteries. As you can see here in the presentation, we are studying different materials, including titanate, oxide, phosphate, sulfate. These materials we are trying either to enhance their morphological properties, structural properties, in order to increase their performances as much as possible. Why we need batteries and why energy is one of the hot topics in the world actually, because there is a dramatical increase of the energy demand in the world. Why? Because the population, for example, in 2000, we were only 6 billion, but after 30 years, it's expected to increase to 8.2 billion. So this increasing of the population number will increase the energy demand, but also many environmental issues. So we have either control and offer sufficient energy and also avoid all these environmental issues which comes from this energy development. So one of the ideal solution actually is to use of the battery in order to store the energy coming mainly from renewable energies, for example, solar energy, wind energy. Why? Because all renewable energies are intermittent. So, for example, solar energy, we have energy only during the day, but during the night we don't have it. So we need to store it and use it when it's needed. So lithium-ion batteries dominated battery market since 30 years because it offers the high density energy, but actually it cannot fulfill all the needs in the market. So there is development of other alternatives to search for cheaper, high energy density and more sustainable battery energy. Mainly the substitution of the cobalt, which is the most toxic element in the lithium-ion batteries, and also lithium. Now research are moving toward sodium, potassium, zinc-ion batteries, which offers better sustainable alternatives to lithium-ion batteries. These batteries are used in different applications, portable electronics as your computers that you are using now. But one of the main utilization of batteries is the automotive, because we have actually a dramatical development in the use of electrical car. And in Europe, it's expected in 2030 to have 50% of the car that they are electrics. Also, we have to store energy from renewable energy sources. And actually, there is also future application of battery. For example, for health, we need also flexible batteries for flexible electronics. So in our lab, we have different process in order to prepare materials. One of them is pre-drying process that we are using. Why? Because it offers many advantages. We can spray dry suspension or solution that we can inject from here, and we can collect it at different points depending on the particle size of the materials. And actually, there is an increase of the publications where we report the preparation of the materials using spray drying method. We can also control different parameters using this method, either the pressure, the temperature of the drying, and also the nozzle type. We have different nozzle type, as you can see here in the presentation. The main advantages of this method is we can control the morphology of the particles that we are preparing. Depending on the final application, we can either prepare porous particles, hairy particles, hollow particles. So we can use it in the wide range of application, and one of them is batteries. Here I will give a presentation on sodium vanadium fluorophosphide in VPF material, one of the most promising cathode material for sodium-ion batteries. And for example, in France, Tiamat already started to use it for commercial application. Why this material is one of the best material? Because it has very high stable structure from work. It has very high ionic conductivity thanks to its structure, but also it has very high theoretical capacity, because either we can extract 2 or even 3 sodium, and we can reach by that very high capacity. The main drawback of this material is the one of the phosphate in general is its low electronic conductivity. But we can, by using spray drying method, prepare in one step this composite material by the addition of the carbon sources and the suspension of the precursor. And when we spray dry it, we'll prepare in one step this composite material. Indeed, for that, we have to make different optimization to prepare pure and well crystalline material. We have to optimize the precursor materials. We have to make the optimization of the spray drying parameters, and also we have to make the optimization of the heat treatment to prepare pure material without significant impurities, which is one of the main factors that determine the electrochemical properties of the material. This one, for example, is the picture of the spray dryer machine that we have at GreenMat. We have actually 2, one which is working under air, but this one is, we can make the spray drying under controlled atmosphere, mainly for the air sensitive or water sensitive materials. We can even make the spray drying of nanoparticles without any problem. So in the case of NVPF material, we mix the precursor based vanadium, phosphorus, and also we add some carbon sources. Then when we mix them, we have two steps. Either we can prepare the pure material without the addition of the carbon sources, or we can add the carbon sources in order to prepare this composite material, and then we make the spray drying and the heat treatment. For example, for the pure material, when we add only the stoichiometric amount of the NaF, which is the source of the sodium that we use here, we can see that we have many impurities, but when we increase it to 3.5, we can see that we have only this sodium carbonate that we can remove easily by washing the material in water. We prepared also the material with carbon nanotubes, and we can see that by addition of 3.5, we still have many impurities. We increase it to 4, we have this almost pure material, and with only a few traces of sodium carbonate that, as I mentioned, we can easily remove it and to prepare pure material by washing the final product in water. We also studied the effect of the heat treatment temperature. You can see the as prepared material here is the spray dried material, is the mixture of the precursor that we heat at different temperatures, starting from 500 until to 600, and we can see it's only at 600 degrees that we have the pure material, but before that we have still some rest of impurities. And we have also the good distribution of the elements. You can see here sodium, vanadium, and phosphorus, and fluor, which means that spray drying allows to prepare particles with homogeneous distribution of all elements. But the main difference for the material with and without carbon nanotubes, with carbon nanotubes, we have this flower and morphology, but without carbon nanotubes, we have these nice spherical particles, which means that the addition of the carbon nanotubes has great effect on the morphology of our NVPF material. When we start to go up on temperature, in order to try to increase the crystallinity of NVPF material, we can see that we have some degradation of the material. So we stop the calcination only at 600 degrees. Compared to the methods that are used in the literature, we can see that we have spray drying method offer lower temperature with very low heat treatment time, which is one of the most critical parameter, because, for example, using solid state, we need between 8 and 30 hours, which is energy and time consuming, which is not suitable for industrial application. Then we make the electrochemical test of these two materials, first with versus lithium, and we can see that the material with carbon nanotubes shows higher capacity at different C rates, starting from C over 15 until 10C, compared to the material without any carbon addition, which means that carbon nanotubes increase the electronic conductivity and thus increase the electrochemical performances. But we can see that we are a bit far from the theoretical capacity, and in order to increase more the capacity of our material, we make the grinding of the particles in order to increase the surface area. And we can see after the ball milling, the morphology changed completely, and we formed like agglomeration of the nanoparticles by increasing the particle size from 10 to more or less 1 for NVPF, and something like 5 because it's hard to decrease the particle size of the composite material with carbon nanotubes, as carbon nanotubes form very rigid network around NVPF particles, but even that we decrease it to the half almost. We can see that after grinding, only during 30 minutes at 250 RPM, we reached the theoretical capacity for the material with carbon nanotubes, and we still have the big difference between the material, the composite material, and the material without any carbon sources at different rate. This results confirm that the addition of the carbon and the grinding step increase dramatically the performances of the NVPF material. In order to explain the source of this increase, we can see that the charge and discharge voltage profile are different. Here we can see that we have 3 plateaus for the one with carbon nanotubes. And when we make impedance measurements, we can see that the one with carbon nanotubes shows lower resistance, which means higher electronic conductivity. We make also the cycling at 1C, which is very fast regime. It means we are charging and discharging the material in 1 hour. We can see that we have very stable capacity over 100 cycle with almost 100% of the capacity retention for both materials, but with highest capacity for the one with carbon nanotubes. After this positive results using carbon nanotubes, we try to use other sources of carbon. We use carbon black and also graphene. And also in order to decrease the particle size by using only spray drying method, we changed the nozzle type. And we can see that here, the one without any carbon, we have the spherical particles. With carbon black, we can see we have the spherical particles, but with rigorous surface, different surface from the one without any carbon sources, and the one with graphene oxide, it's deformed, slightly deformed spherical particles. You can see for all 3 carbon sources, we prepared almost pure material. We have, as I mentioned, only this sodium carbonate that we remove easily by the grinding in water. We can see here by comparing the electrochemical performances by carrying out the rate capability test, we can see that the one with graphene showed the highest capacity at all series, which means that graphene is of increase much better the electronic conductivity than 2 other carbon sources. We can see, for example, at 1C, we have almost the theoretical capacity of the NVPF material. This extra capacity, because the theoretical capacity is only 128 milliampere per hour, this extra capacity comes from the degradation of the electrolyte that we'll explain later on using XPS technique. In order to increase, again, the electrochemical performances of all these 4 materials, we make the grinding using the same conditions as before, 30 minutes in using 250 RPM. We can see that the morphology changed after grinding for all materials, and the one which is different is with carbon nanotubes, because carbon nanotubes have very rigid and good mechanical properties, which makes the grinding difficult. Here is the TM images in order to see the different source carbon, how they are mixed with NVPF active cathode material. The one without any carbon, we can see only particles of NVPF. The one with carbon black, we can see that carbon black is either at the surface or is interconnecting the NVPF particles. Carbon nanotubes, we can see displaced nanotubes that are at the surface, but also inside the particles. And these graphene sheets are covering the particles of NVPF material. We have also some differences, not only on morphology, but also in the surface area, because we make some BOT surface measurements. And after grinding, we had some surprising results, mainly for the one with graphene, because the capacity decreased at 1C. Why? Because we are making the grinding. Here we make the measurements versus the sodium. When we are making the grinding, we are breaking this graphene sheet, which means that we are inhibiting its positive effect, and that the performance decrease. But the one that is showing best electrochemical performance after grinding is the one with carbon nanotubes, thanks to the positive effect of these carbon sources. Here also we were interested to optimize the voltage of cycling, the voltage window. This is where we make some XPS measurement to see why we have this extra capacity and how we can optimize the electrochemical performances. This is why we make some XPS measurements at different voltage. but mainly at 4.3 and here 4.6. We can see that when we increase the potential to 4.6, we have some differences in the composition of NVPF material, which means that we have some degradation of NVPF, because here, for example, we have two. When we go for vanadium, we go to 4.6, we have 1.4. And also we have some reaction with aluminum, which is used here as current collector, which means we have some side reaction of the electrolyte and active cathode material at high voltage. This is why we were thinking to make only cycling until 4.3, and we can see that we have for almost for all materials only the theoretical capacity, and mainly one with graphene oxide before grinding, and we have very good stability over 200 cycle. Even we are cycling our material there in 200 cycle, we have very good cyclability and acceptable Coulombic efficiency. Compared to these three materials with carbon sources offers highest capacity compared to one without any carbon source, because we can see that the capacity decrease dramatically with cycling and reach almost 1/3 of the initial capacity after 200 cycles. We make also some preliminary tests by using this material as cathode material for potassium-ion batteries. We can see that the one without any carbon sources, after cycling at different rates, the capacity decrease rapidly and reach almost zero at C/4. But the one with graphene oxide and carbon black and carbon nanotubes show high capacity, which are promising results that will encourage us to make more tests of these four materials in potassium-ion batteries. So as a conclusion, we succeed in this work to prepare the pure materials, either without carbon or with carbon black, with carbon nanotubes and graphene oxide by using spray drying method. We can see that the source of the carbon has a great effect on the morphology. And also after grinding, the particle size decreased dramatically, except for the one of carbon nanotubes. We make some improvement, and we got some very competitive results in terms of the capacity and also working voltage for our NVPF material, thanks to addition of the conductive carbon, and also by controlling the cut-off voltage and limiting it only to 4.3. We can see in this table, we got really very good results, mainly for the one with carbon nanotubes and also mainly for the one with graphene. We have almost 100% of the capacity retention, which is the theoretical capacity over 50 cycles or even 200 cycles. At the end, I would like to thank my colleagues from the Green Mat Lab, mainly Nicolas Eshraghi, who is working on this topic. He defended his thesis last year and now he's working in Austria. Our funding agency, FNRS, and also Wallon region. And I would like to thank my collaborators from University of Montpellier in France and Oak Ridge National Lab. And thank you very much for your attention.
Yeah, thank you, Abdul Bata. Okay, thanks a lot. Now the forum is open for discussion. The participants can ask questions in the chat box. Participants, you can ask your questions. I think everybody has understood everything, it seems. Dear participants.
It was clear.
You can ask general doubt also, because he is having a lot of experience and exposure in batteries and various types of batteries.
Mm-hmm.
participants ask questions? Okay, if no more questions means, Dr. Angeline, can we wind up?
Yes, sir. Sure,
Yeah.
sir.
Okay. I thank Dr. Abdel Batta. Am I pronouncing your name correctly?
It's fine. It's okay.
Fine. Okay. But, I thank you for your valuable presentation. You not only presented your work, but also presented about your laboratory and Green Mat Lab. Okay, that is a very good insight in for our youngsters. Okay, especially for our youngsters. So I thank you for taking your valuable time and presenting to the youngsters. Okay, thank you. And I also thank Dr. Angeline for her valuable help in doing this session. And I thank all the participants for leisurely attending this session and asking some questions also. In that too, in the previous session, they have asked a lot of questions in the last contributory paper, but I'm not sure why they have not asked questions now. Anyway, it is fine. Okay, you enjoy your day, and we can meet tomorrow, I suppose. Anyway, according to the organizers. Okay, I also thank the organizers for their valuable things. Okay, thank you. Thanks a lot.
Thank you, sir.
Yeah, thank you. Whether any more session is there today, ma'am? No?
No, sir, this is the end of
The
today's
session.
session.
Okay. So we can meet tomorrow.
Yes, sir. With this, we'll close this session. I thank the chairperson, Professor Kingsley, and also the invited speaker, Dr. Mahmood, and all the contributor lecture speakers. Thank you, one and all. Have a nice day.
Thank you.